All right, good morning, everybody. We survived ACTs. Woohoo! I know that Rachel and Isaias didn't have to take it because they're lucky seniors, but the rest of us survived. Woohoo! All right, looks like there's some major audio issues going on right now here in Blackboard Collaborate. So I'm going to take that webcam off and fingers crossed, hopefully that helps. All right, so let's get started here. I think Rachel might be having some audio issues right now. I'm not quite sure if she can hear me or not. Um, Hopefully she can. But anyway, if you showed for both days of testing for ACTs, you should receive a form, a Google form to fill out for your final exam exemption pass. So I know Tommy has filled that out. I sent that to Rebecca. Um, Charter, I know Callie, you're scheduled to take it still. Charter, did you show for both days of testing for ACTs this week? If you need the pass sent to you or emailed to you, let me know and I can send that to you so you can get that Google form. So if you didn't receive the Google form from your proctor, just email me and I can get that sent to you so that you can fill that out if you've completed both days of the ACT testing. Okay, only fill it out once though. Even if you're sent it multiple times, just make sure you're only fill it out once. All right, so it's been a while since I've seen you guys, a whole week actually. And today, like Isaiah said, we're entering the matrix. Woohoo! We will need a calculator at some point. I'm going to show you how to do it algebraically, but a calculator is going to save us a lot of time. We may not actually look at our calculator too much until next week, Tuesday, I want to say. I think I'll spend most of the time showing you how to do things algebraically here today. But next week, yeah, if you don't have a graphing calculator, you might want to find one before next week so that we can use those operations of matrices on the calculator to help us out. All right, before we begin today, were there any questions though regarding 7.01? All right, don't forget the test correction opportunity is still out there. So if you need to do test corrections, feel free to do so from that Unit 6 test. We are going to venture forward here, and 7.01, just to refresh us a little bit because it's been a while since we've talked, but 7.01 we looked at systems of equations. So the systems of equations we looked at were no longer just linear equations, but they could have been parabolas or lines or cubic functions or sine waves. So we really kind of expanded our horizon a little bit there on what we would look at for our system of equations. All right, today we're going to take a look at matrices like I had mentioned. The whole point of matrices is that it's another method to help us solve a system of equations. Before we get to that part though, with finding out how we're going to use the matrices to solve systems of equations, I have to introduce you to matrices and what they actually are first, because we have never seen matrices up to this point. So if you've had me as your math teacher prior to pre-calculus, we have never looked at matrices before. It's kind of an obsolete topic because we know so many other methods to help us solve our system. So we know the substitution, we know the elimination, we know graphing. We didn't really need to focus on matrices at that point. In fact, we don't actually need matrices now either, but it is just another tool that we can put in our bag and use when needed if systems of equations do pop up. So we are going to go ahead and take a look at our matrices today and what they actually are. And there's a lot to know about them, believe it or not. The first piece of information we have to know is how can we define our matrix here. So our matrices are defined by rows and columns. All right, so how we will identify this is we always call a matrix an M by N matrix. So M stands for the number of rows. So remember, rows are things that move left to right. So rows go left to right horizontally. And that is going to be your M right up here. N is going to be the number of columns that that matrix has. So a column, and I'm sure I spelled that right. A column is one that moves up or down. All right. So that's how we're going to classify our matrices. And that's the first thing we always want to look at is how many rows and how many columns does our matrix have, because that's going to play a really important role when we look at the adding or the subtracting or the multiplying of our matrices together. There's going to be certain guidelines we have to follow depending on the order of the matrix there. All right, so in the matrix, and again, this is just a very generic example here, we have elements or entries, so individual elements or entries within the matrix here. So here you'll see A sub 11. That actually means A row 1, column 1. So the 11 here is actually denoting the row and the column that it's appearing in. So A sub 11 is actually a row 1, column 1. And if I look down here, A sub 22, that's really the element in row 2, column 2. So that's how we read those tiny subscripts. Okay, sorry, I had to sign out of Hangouts because they're going crazy all of a sudden here, so I apologize for that little delay. All right, I'm sure that you are already reading through the rest of the bolded areas here, but the order of our matrix, that's what we were referring to with the M by N. A square matrix is when M and N are the same values. So if you have a 2 by 2 or a 3 by 3 or a 4 by 4, that's what we consider a square matrix. And then two matrices are equal matrices if they have the same order and their corresponding elements are equal. So that means that all the elements inside the matrix will be identical to each other. All right, so let's go ahead and just get practice with determining the order of a matrix. And like I said, this is going to be a very important piece to it all because we need to identify order before we can add or subtract or even multiply matrices together. So let's go ahead and just get our practice with the order of a matrix. So remember, the order is M by N. M is distinguishing the number of rows, and N is distinguishing the number of columns. So let's start with this first one. How many rows are there and how many columns are there? Because that will help us with the order. There are 2 rows. Yeah, there you go. So 2 rows, right? So our first value is going to be a 2. And there are 3 columns. So this is a 2 by 3 matrix. This is not a square matrix, right? Because 2 and 3 are not the same value. So this is not a square matrix. What about part B? What is the order of the matrix in part B? A 4 by 2? Good. There are 4 rows. 1, 2, 3, 4, and 2 columns. Awesome. And then matrix C, what's the order for matrix C? Three by 3, yeah. This is a square matrix, right? Because the number of rows and the number of columns match. 3 rows and 3 columns, so this is considered a square matrix. Good. Any questions with determining the order? Because like I said, believe it or not, that's actually going to be a pretty important piece moving forward. All right, so here's why the order is so important. If we want to add or subtract matrices together, they must have the same order. If your 2 matrices that you are trying to add or subtract together do not have the same order, you cannot add or subtract them, right? It cannot be done. The other type of multiplication that we're going to start off with is just scalar multiplication at this time. We will go ahead and actually look at multiplying 2 matrices together a little bit later today. But to start us off, we're going to start with scalar multiplication. Scalar multiplication is when you just take that value and you multiply it by every element inside the matrix. So it's nothing too spectacular or too challenging. So scalar multiplication is just taking the value and multiplying it by every element inside the matrix. When we go to add or subtract matrices together, and they must have the same order, we just add the like elements. So we'll add the elements in row 1, column 1 together. We'll add the elements in row 1, column 2 together, and so forth. Or we'll subtract those elements together to get the resulting matrix. Woohoo! I don't know if they actually appeared on the ACTs. I didn't look at the test, so I'm not sure if there were any matrices questions actually on the ACTs or not. Yeah, I didn't think so. It's kind of becoming an obsolete topic, so we don't really see it too much because we have other methods for solving our equations, which is generally when we'd see our matrices. All right, so let's go ahead and practice a little bit with some of these operations. Before we do that, I'm just going to have us understand what element they're referring to. So what element is in the A sub 12 spot, which is actually means what element is in row 1, column 2. Careful, row 1, column 2. Yeah, so row 1 is this row right up here. And then column 2 is right here. So what's the only number that is kind of the intersection of those? That's your 9. So 9, that's a really bad 9, sorry. 9 is the element that is in row 1, column 2. What element is in row 2, column 1? So A sub 21. Now it's 6. There you go, right? So row 2, column 1, that's our 6. What about A sub 32? What element is in that spot? There isn't one. Yeah, it's an error. There's no element there. So we would just write does not exist. So sometimes they might try to trick us a little bit and ask us for an element that's not actually there. Yeah, so there's no row 3 in this matrix. There is a column 3, but not a row 3. So there's no element in that spot. So you can't find it. All right, let's go ahead and put together the multiplication here and our addition piece. So first, let's identify what element is in A sub 11. So row 1, column 1, that's element 1. What about A sub 22? What can I replace that with? Yeah, row 2, column 2 is 2. And what about A sub 23? So element in row 2, column 3 is 11. Good. When I go ahead and perform these operations, remember multiplication before addition. So we'll multiply those first and then add them together to get a grand total of 35. Perfect. Any questions with that at all? So not too bad if we're able to identify what these little subscripts actually mean and what they refer to. Okay, here comes, oh yeah, it's the fun part, not quite the real fun yet. We haven't gotten to that quite yet, but let's go ahead and add, subtract, and then we'll multiply with our scalar. These, you wouldn't really necessarily use like your matrices here too much in real life outside of like an engineering maybe degree, because we have so many different options to help us solve our systems of equations. This is just another tool to help us organize information. So I'm not quite sure if there would be too many careers or when you would necessarily use this in the real world other than helping you just stay organized with your information. That's why we really haven't seen it before this point either, is because there are a lot of other methods that are more handy that we can use instead. But it is a great tool to maybe organize information a little bit better than some of the things we've seen in the past. So, yeah. All right, let's go ahead and before we can add or subtract matrices, we need to make sure their order is the same. So, do they have the same order? If so, what is the order of each of these matrices? Yeah, they're both 2 by 2s. Yep, so if they're both 2 by 2s, we can go ahead and add those together. So when we add them together or subtract them together, we're looking at the elements that are in the same spot. So we'll start with the elements in row 1, column 1, and now you would add those elements together. So what if I'm going to add in my resulting matrix, what is that new element going to be? An 8, good. What is the next element going to be in row 1, column 2? A 6. Then we'll jump down to row 2. So row 2, column 1, 15. And then lastly, row 2, column 2. Yeah, so really this is just adding. If you can find the like elements there, you just add them together. Same thing with your subtracting. Just make sure you're doing matrix A first and then subtracting off the matrix B. So what's going to be our resulting matrix in part B here? So let's start with element row 1, column 1. -6, good. What about row 1, column 2? All right, row 2, column 1, and row 2, column 2. Awesome. The last one, because it is just scalar multiplication, we just multiply every element in matrix A by the -5 to find our resulting matrix. So what is row 1, column 1 going to be? Row 1, column 2, row 2, column 1, and row 2, column 2. Yeah, so notice we just took matrix A and multiplied every number in there by -5. So -5, -5, -40, -20. Good. So these are kind of our basic operations. They're what we can do really quickly if the order is the same. Now, order doesn't necessarily matter with your scalar multiplication, right? You can just take whatever matrix you want and multiply by that scalar that's out in front. Now, if everything were to stay that easy, unfortunately, it gets a little bit more complicated when we actually try to multiply matrices together. So if we're trying to multiply matrices together, the first thing we have to do is look at their order. So this is a little bit different than the adding and subtracting, and I'll show you what they mean up here in the definition of our matrix multiplication. So the first thing we have to do is look at the order of matrix A. What is the order of matrix A? That's a 2 by 3 matrix. What is the order of matrix B? A 3 by 2. Okay, notice these are not the same, and that's okay. We don't have to have the same order in order to multiply our matrices. What has to happen here when I take a look at these orders is the middle numbers right here when they're back to back need to be the same. So I have a 2 by 3 and a 3 by 2. Those 3's in the middle are the same, therefore I can multiply the matrices together, and my resulting matrix will be a 2 by 2 matrix. So my answer is going to be a 2 by 2 matrix once everything is said and done. All right, so knowing that it's a 2 by 2, I'm going to kind of create a really large matrix here that just has 4 elements in it, right? It's a 2 by 2 matrix, 2 rows, 2 columns. The two numbers, outside numbers, do not have to be the same. No, just the 2 inside numbers have to be the same. Yep, so just the 2 inside numbers. And you do want to follow the matrix, the order in which you're multiplying, right? So we had to look at matrix A first because that's what came first in the multiplication. Then we had to look at matrix B second. So the order in which you're multiplying here does matter as well when you're trying to figure out if you can actually multiply these together. If the middle numbers were not the same, you cannot multiply the matrices together. It will not work. All right. All right, let's actually show you how to find the 4 elements in our 2 by 2 answer. All right, so what we're going to do is we're looking for row 1, column 1. So I'm going to take the elements from row 1 in matrix A and column 1 in matrix B. And what I'm going to do is I'm going to multiply the elements in order here. So I'm going to do 2 times 1 plus, and the 2 came from right here. The 1 came from over here. Next, I'm going to take the second element in each highlighted area. So 1 times 0. And then I'm going to add that to the third elements multiplied together. -3 times 1. Okay. That's kind of confusing. And this is where I said the matrices get a little bit fun on how we can actually find these answers here. So now we're going to simplify this. We get 2 plus 0 minus 3. So what is 2 plus 0 minus 3 when I combine that? That's a negative 1. So the first element in row 1, column 1 simplifies down to a negative 1. All right, next thing we're going to do is we're going to find row 1, column 2. So I'm going to move my highlighting over a space, and I'm going to kind of do the same thing here. We'll multiply the first elements together, so 2 times negative 4. Multiply the second elements together, 1 times 2. And multiply the third elements together, negative 3 times 0. All right, I do want to simplify those, so that's a negative 8 plus 2 plus 0. What's a negative 8 plus 2 plus 0? Negative 6. So that's going to be my element for row 2, column 2. Next, we're going to go ahead and find row 2, column 1. So row 2 we start with, and column 1 from the second matrix. And the process starts over. We'll start with the multiplying the first elements together, multiplying the second elements together, and multiplying the third elements together. When you simplify that, what do we get for row 2, column 1? Yeah, just a 2. And this is time consuming, right? It's not necessarily difficult, but it's time consuming to get our answers. All right, the last element we need is by looking at row 2, column 2. So I'm just going to switch the highlighting there in part B. And the process starts over. 0 times negative 4 plus 1 times 2 plus 2 times 0. All right, and what will that simplify to? A 2. Good. All right, so there is our resulting matrix after we multiply these two together. Phew, that was quite the process. Any questions with how we did that? So it takes some time to get used to, that's for sure. But once it's a very repetitive I lost my train of thought here. It's a very repetitive process. There we go. So once we get the hang of it, hopefully it'll go pretty quickly. All right. Now we're going to go ahead and see if we can do A times B and B times A. Well, before we can actually venture forward with the multiplication, we have to check the order first. So let's take a look at the order of A times B. What is matrix A? So what is the order of matrix A? That's a 3 by 2. What is the order of matrix B? A 2 by 3. Can we multiply these two matrices together? We can. Yep, notice that the middle numbers are the same, which means the resulting matrix is a 3 by 3. All right, usually that's a little intimidating, but actually it's not going to be that bad. The first thing I'm going to do is just set up the 3 by 3 matrix. So we need 3 rows and the 3 columns. Setting that blank matrix up kind of helps you figure out like what numbers to kind of multiply together through that process, and hopefully makes it a little less overwhelming when we go through it all. So let's start with element in row 1, column 1. And notice that it's a little bit shorter here. We're only technically multiplying and adding two values together. So we'll start with negative 2 times negative 3 plus 3 times 2. All right, what is that going to simplify to? That's a 6. Oh, I think it's actually going to be a positive 6 plus positive 6 because of that double negative in front. Yeah, I was going to, 0. But I think that's going to be a 6 plus 6 when we look at that. All right, let's go ahead and move to the middle. So we're still in row 1, but now we're looking at column 2. So we've got negative 2 times 3, which is 6, plus 3 times negative 1, which is your negative 3. What is 6 plus negative 3? Maybe, yes. Let me double check. Negative 2 times 3 is a negative 6. Okay, yeah. Whoopsie. Missed that one. So that'll be a negative 9. There we go. Good catch. Very good catch. All right, let's go ahead then and take a look at row 1, column 3. So careful of my signs here. Negative 2 times negative 5, positive 10. 3 times negative 3, I believe that's a negative 9. So I think I did the signs there correctly. 10 minus 9 should be a 1, right? Good. Then let's go ahead and we're finding row 2, column 1. So I'm going to just change the highlighting over here. We'll have a 15 plus 6. Does that look right? And just for time's sake, I'm going to speed up a little bit. So because I'm speeding up, definitely watch for errors with my signs here. All right, anybody see any mistakes in row 2? All right, if not, I'm going to venture on to row 3. See, that's a 9 plus 5. I think we get a 0 as our end result there. Again, double check those values. I don't think I made any errors along the way after that first element. All right, any questions with how we got that resulting matrix? All right, then my question to you is, if I reverse the order here, A times B and B times A, will I get the same result? No, Tommy says no, we're not going to get the same result. Yeah, because actually the whole matrix itself would take on a different order. Because if I switched around those matrices, now we're taking a look at a 2 by 3 and a 3 by 2, which means your end result is a 2 by 2 matrix. Yeah, so you are not going to get the same result by just switching them around. So order does matter in which we're multiplying here. We're going to skip that second part B only because of time constraints right now. And we're not going to quite go over that since I have a few more topics to touch upon still before I let you go today. But just note that the order in which we multiply matters. So A times B is not going to give you the same end result as B times A. Unless the matrices themselves are inverses of each other. But we'll get to that in a little bit. All right, questions with that at all? So how do we determine what the order of the product is going to be when you multiply your matrices? So you're going to be looking at those middle values of the order, and that's going to tell you whether you can multiply them together or not. Right? So because they're both 3's in here, you can multiply them together. Right? So the resulting order would be the numbers left on the outside. So we would get a 2 by 2 matrix for the end result. Right? And the same thing that happened up here, the 2's were the same. So we knew that our end product was going to be a 3 by 3 matrix because those are the numbers that came from the outside. Exactly. Yep. That's exactly what it would be, Zayas. Yep. Awesome. I know, kind of the first time that we heard that multiplication isn't necessarily commutative. Good. Now, we do have something called the identity matrix, and you heard me allude to the inverse matrix at the end of that last example. I said that you would not get the same product unless your matrices were inverses of each other. If they are inverses of each other, when you multiply A times B and B times A, your product would be something called the identity matrix. The identity matrix is composed of two numbers only, 0 and 1. All right, so your identity matrix basically has 1's along the diagonal, and we call this the main diagonal because that's kind of how you draw your X, right? You always move in this direction when you make an X. So that's what we call the main diagonals. If you were to multiply this direction, that's called your minor diagonal, right? So when you make an X, I would say that most of the population makes their X's by drawing this line first and this one second, right? So this first line is the major diagonal, and the second line is the minor diagonal. So you're going to hear that term used coming up here when we talk about the determinant, I believe. I knew you would be backwards, Isaias. I knew that you would do it differently. So you're going to have to get used to multiplying from kind of left to right, right? So that's the thing that you're going to have to keep an eye out for. Most of us, if we draw our x's this way first, you're going to be probably just fine with finding your determinant coming up. All right, so anyways, that main diagonal is going to be consisted of your 1's, and everything else in the matrix will be 0. So every other element will be 0. If that's occurring, then we know that we have an identity matrix present. Okay. And like I said, the only time where your matrices are commutative, multiplication is commutative, so A times B equals B times A, is if these are inverses of each other. And you'll know that they're inverses of each other because their product will be this identity matrix. So on the last slide, if these would have been inverses of each other, our product would have 1's on the main diagonal and then zeros everywhere else. So that's what our end result would have looked like if these were inverse matrices. Obviously, they were not inverse matrices because when we multiplied A times B together, we did not get this identity matrix. We got nothing close to it. You will notice that not every square matrix has an inverse. And that's another thing that we should present or look at, that I'm trying to see here if we're just looking at square matrices for these or not. But if a square matrix does have or does not have an inverse, then we call it singular. If it does, then it's non-singular. We don't really focus on these vocabulary terms too much, to be honest with you, but in case they pop up on a homework assignment or something, just as a vocabulary piece, it might be good to know what those mean. But honestly, we're not really going to pay attention to the singular versus non-singular after this slide. All right, I did mention that we can actually do scalar multiplication, or not scalar multiplication, matrix multiplication using our calculator. I think there is a PDF file, it says, in the online lesson to help you with this. We will also be looking at how we can do matrices on our calculator in Tuesday's class. So we will focus kind of more on how we can speed the process up by punching these matrices into our calculator and then relying on the calculator to help us with the multiplication piece and the inverse piece as well. So that'll be really fun to do in Tuesday's class, because we're going to be like, man, that was so much faster. Why did we have to learn how to do it all by hand if the calculator can really do a big portion of it for us? But it'll be important to learn how to do it by hand as well. The next thing we're going to talk about is the determinant, and I'm going to go kind of quickly through the last two concepts here. The determinant of a square matrix can be found by basically multiplying along the diagonals. So you start with the main diagonal first, so A times D, and we subtract off the minor diagonal, which is B times C. So main versus the minor diagonal there, and that's going to help us find the determinant. All right, the determinant is important because if it's not 0, if the determinant is not 0, then that original matrix has an inverse. And to find the inverse, you're going to take 1 over that determinant and multiply it by the original matrix kind of inverted a little bit. So notice that when they are multiplying it by the matrix, they're switching the values on the main diagonal, right? So it no longer goes AD, but they switch that to DA. And then on the minor diagonal, they're taking the opposite of the values. Okay, so again, this will be important if we're asked to find the inverse of a matrix. If we're asked to find the inverse of a matrix, we want to follow this procedure. So first find the determinant. If the determinant is not 0, you can proceed forward by switching the main diagonal and taking the opposite of the minor, and then multiplying through by 1 over that determinant. Seems a little bit weird, but it's really not that bad of a process when you actually do an example of it. And again, there is only an inverse if the determinant is not 0. If you do get 0, there's no inverse for that matrix, right? So that would be considered singular if there's no matrix for it. This only works for square matrices, by the way, as well. So you've got to have a square matrix present to find the inverse of that. If it's not square, you cannot go find the inverse of it. Okay, I want to jump around here and talk about how we can find the determinant of a square matrix. They gave us an example of a 2 by 2 with the diagonals there. You just did your main diagonal minus your minor diagonal. But what if there's more than just 4 elements present? So like in a 3 by 3 matrix, how do we do that? Well, what you have to do in a 3 by 3 matrix is copy the first 2 columns over. So notice I'm going to take column 1 and copy that over, and the same thing with column 2. And the reason for this is when I go to find the main diagonals, there should be 3 of them, right? Not just 1, but 3 now. So essentially what we have to do here is we are going to multiply all the pink diagonals together. So 4 times negative 3 times 1. That's your negative 12. And we're going to add that with all the other pink diagonals. So 4 times negative 1 times 3. That's another negative 12. And 1 times 3 times 0. Anytime there's a 0 in the list, we really like that. So the first main diagonal is going to simplify down to a negative 24, right? I believe that's what that's going to come down to. And then we're going to subtract off the minor diagonals. Now, when we subtract off the minor diagonals, remember that's going the opposite direction. I start at this corner and kind of work my way backwards. So 1 times negative 3 times 3 is a negative 9. 4 times negative 1 times 0, that's our 0. 4 times 3 times 1 is a 12. So negative 9 plus 12 is 3. Negative 24 minus 3 is a negative 27 for the determinant of that matrix. That means that because the determinant was not 0, there is going to be an inverse for this matrix. Okay. We're not going to find the inverse of this matrix, but there is one. Okay. That was kind of a lengthy process, and I wanted to go through one of those in the class here today because they did not show how to do that in the textbook at all. So they show you how to do a 2 by 2 determinant, but they didn't show you how to do a 3 by 3. So I did want to show you that that can be done by expanding the 2 columns here and looking at it that way. Okay. The good news moving forward, we can also do determinants on our calculator. So that's the good news moving forward, is that in the next lesson, we'll figure out how to do that on our calculator as well. Or if you want to take a look at that PDF that's in the online lesson, I think it shows you how to find the determinant in there. The last thing, and this one's really, really quick, it does say to solve for x where a equals 3, 4 and b equals 15, 1. So what we would do there is we would just set up 2 different equations to help us solve for this unknown matrix. So this x is an unknown matrix, and it looks like it's a 2 by 1. So there's 2 elements that we've got to find for this matrix X right here. So when you have an unknown matrix, we're just going to set it up in the same order that the others have. And I'm just going to copy in the rest of the problem here. And then we can just read it right through, so I can actually create an algebraic equation from this. 4 times x plus 3 equals 15, and 4 times y plus 4 equals 1. So once you set up those two equations, you can then just work backwards to solve for x and y in each equation. So subtract 3, divide by 4. I think you get x equals 3. And then in the second equation, subtract 4, divide by 4. I think that gives you a negative 3/4, right? So that x matrix that they're looking for is 3 and negative 3/4. So if you can change it to a linear equation that you already know how to solve, it'll go pretty quick. Okay, yikes. That was a lot of information that we threw at you in the last 50 minutes. But we did cover all kind of the major topics from this 7.02. But there's a lot of information that goes on in this lesson. And we obviously didn't get to practice as much as we would have liked. So take a look at those. Try to work your way through that homework assignment, and I'll definitely be showing you how to do this process on the calculator starting next week. All right, if you want to take a look at that PDF that I threw in the online lesson to get a head start on that, you can. But I will definitely show you how we can do that on the calculator to speed things up as well in Tuesday's class. Along with some other interesting things we'll look at in Tuesday's class as well. All right, any major questions regarding the matrices so far? Okay, hang in there. We'll get through it all. But like I said, there's a lot of information that's thrown at us at the starting of our matrices here. All right, that's all I got for you, so I'll let you go. Have a great rest of your Thursday, and I'll see you guys all again Tuesday. Bye, everyone.
Recording stopped.